Morning class, or good afternoon. Yeah, it's the afternoon now. Today's Wednesday, June 10th of 2020. Day 45 of Coronachem, period 1. This is the second half of the mock test answers that I assigned a couple days ago. Let me read you the question. Number 497. Lanthanum metal forms cations with a charge of +3. Consider the following observations about the chemistry of lanthanum. When lanthanum metal is exposed to air, a white solid, compound A, is formed that contains lanthanum and one other element. When lanthanum metal is added to water, gas bubbles are observed and a different white solid, compound B, is formed. Both A and B dissolve in hydrochloric acid to give a clear solution. When either of these two solutions is evaporated, a soluble white solid, compound C, remains. If compound C is dissolved in water and sulfuric acid is added, a white precipitate, compound D, forms. A. Propose identities for the substances A, B, C, and D. B. Write net ionic equations for all the reactions described. C. Based on the preceding observations, that what can be said about the position of lanthanum in the activity series. Okay, we'll do one part at a time. The first one is when you mix lanthanum with air, you get a compound we call it A. It's obviously the oxide, because oxygen, a non-metal, tends to react with metals, and it has the highest electronegativity of the things we normally find in our atmosphere. The only thing that's a higher electronegativity than oxygen is fluorine, but we don't find fluorine in any quantity in the atmosphere. So anyway, lanthanum reacts with oxygen, you get lanthanum oxide. Because lanthanum is a +3 charge and oxygen is a -2 charge, you're going to get 3 oxygens combining with 2 lanthanum cations, and you'll get lanthanum oxide. That's the most sensible answer to that question. Compound B, when you throw lanthanum in water, it reacts to form a hydroxide. The bubbles are undoubtedly hydrogen gas, which is being reduced from a +1 oxidation state in the water molecule to 0. So that's actually giving us a clue about where lanthanum sits on the activity series. Clearly, lanthanum is higher in activity than hydrogen because it's able to pass its electrons down to hydrogen. Remember the activity series I taught you when you learned the periodic table? It was, I gave you a mnemonic: Lick, Bacana, Magalman, Zinker, Fico, Nisin, PBH, QAG, Hug, Patau. Hydrogen is kind of in the middle. They've assigned hydrogen an oxidation state of 0 because a good part of the elements are higher than the oxidation, higher in activity than hydrogen, and a good number of the elements are lower in activity compared to hydrogen. So hydrogen appears in the middle. They arbitrarily assigned it an oxidation state, an oxidation voltage of 0, or a reduction voltage of 0, either way. So compound B would be lanthanum oxide, hydroxide, lanthanum hydroxide. Then they took the 2 things that were made, A and B, there's A, there's B, and they added hydrochloric acid to both of them. The result was a solution that when you dehydrated, it produced a white solid that we called C, and that has to be lanthanum chloride, because what happens? The lanthanum cation combines with chloride, you get lanthanum chloride, 3 chlorines to every 1 lanthanum, because +3 for the lanthanum, -1 for the chloride. Same thing happens here to give you lanthanum chloride, except now it's combining with 3 HCl's as compared to 6 HCl's, because there's 2 lanthanum cations in lanthanum oxide. So both the oxide and the hydroxide will react with hydrochloric acid. When you dehydrate the product by removing the water, you get lanthanum chloride. So that is the identity of compound C. Next, we have the lanthanum chloride was taken and reacted with sulfuric acid. So what you would get is lanthanum sulfate and hydrochloric acid as a byproduct. So the thing we're interested in is the lanthanum sulfate. And the sulfate is a -2 charge, if you remember your polyatomic ions. So if you have a -2 charged polyatomic ion, it's going to combine with 2 + 3 lanthanum cations. So compound B is lanthanum sulfate. Then in part B of the question, they ask us to write the net ionic equation for those reactions. For parts 1 and 2 of part B, it's the same. These are the net ionic equations. I wrote them already. So these two are the answers for these two, same as above. And now I'll show you parts 3 and 4. If you need a review on this stuff, you can look up equations. There's a playlist on equations, and it shows you how to write the molecular, the ionic, and the net ionic equations, which you should be fairly familiar with by now. Okay, so part 3. You're going to need lanthanum oxide plus 6 HCl's aqueous. Gives you 2 lanthanum chlorides plus, and this is going to be aqueous, 3 water. When you, this is the molecular equations. Now if you show the ionic equation, you're going to show everything that's reacting split apart. So the lanthanum will turn into 2 lanthanum cations, and you're going to have 3 oxides, 6 protons, 6 chlorides. Then you're going to get still 2 lanthanum AQ plus 6 chlorides, again, AQ, and then the 3 waters. So the net equation here, the net ionic equation, the lanthanum is going to cancel, the chloride is going to cancel, and what you would get is 3 oxides combining with 6 protons to form 3 waters. As it turns out though, oxide is not a stable anion. So what's really happening is that this reaction happens. You're going to get oxide combining with water, because water is the bulk solvent here. It's going to pull a proton off the water, and you're going to get 2 hydroxides. And then the 2 hydroxides that are in solution are going to react with the 6, we had 3 oxides, so we're going to have 3 oxides reacting with obviously 3 waters. So you're going to get 6 hydroxides, and then that's going to react with the 6 protons, and you're going to get 3 waters. Why am I getting 6 waters here? Yeah, right, because there's 3 oxygens here, 3 oxygens there, so it makes sense. But you get 6 waters here, the way I've written it out. So I've thrown in an extra, I'm trying to balance it, but I'm making it worse.
Anyway, suffice it to say that the net reaction is oxide plus water gives you hydroxide, and then the hydroxide is combining with a proton to give you water. That you put it in the lowest terms anyway. So I muddled something there with the numbers, but the net equation is that anytime you have an acid-base reaction, which is what this is turning out to be, because the oxides of cations form hydroxides in aqueous solution. Because it produces a soluble salt, it doesn't actually appear in the net ionic equation. The actual reaction is a reaction between hydroxide and proton, hydroxide and proton to form water, which is what all acid-base reactions basically reduce to. Anytime you have an acid-base reaction, you're going to have hydroxide reacting with a proton to form water. This is your net ionic equation for part 3. It actually leaves it right out of the picture. And then for part 4, I even make a note here. I said, it is doubtful that oxide anions exist in aqueous solution for any length of time, but that is what appears to be happening once the reaction is done. And then remember, they added a step here where they dehydrated, because if the lanthanum chloride is soluble, which I think it is, you're not going to get it unless you dehydrate it. You have to take away all the water to make sure that you get that precipitate. So the fourth one is necessary to erase. Okay. Two lanthanum chlorides reacting with 3 sulfuric acids, and the result is lanthanum sulfate, La2SO4. That's going to form a solid, and you get 6 hydrochloric acids as a byproduct that's going to be soluble. This is also soluble. So if you write this is the molecular equation. The ionic equation will be 2 lanthanum cations, aqueous, plus 6 chloride anions, aqueous, plus 6 protons, aqueous, plus 3 sulfates. Oh, I forgot to put this properly. SO4 has to have 3. 3 sulfates with a -2 charge, aqueous. No, sorry. On the other side, yeah, okay, we haven't reached that part yet. Then you're going to get your lanthanum sulfate. That's going to be a solid. And then your 6 protons are still in solution, and so are your 6 chlorides from the HCl combining. So this cancels in the net ionic equation, and what you get is 2 lanthanum cations combining with 3 sulfate anions to form a lanthanum sulfate precipitate. Okay, and that concludes that part.
The last part of the question I think I already answered, but let's repeat it. 97C, it asks, based on the preceding observations, what can be said about the position of lanthanum in the activity series?
Well, if you get a reaction, like we did in the first case, when you put the lanthanum in water, and they said that hydrogen bubbles out. So that means lanthanum is higher on the activity series than hydrogen. It means that lanthanum can donate electrons to hydrogen, reducing it to its elemental state, which has a oxidation state of 0. So while lanthanum goes from +3 to 0, lanthanum goes from the elemental state of 0 to +3, and the hydrogen goes from plus 1 to 0. Okay, so this is oxidized and this is being reduced, which means the lanthanum is higher than hydrogen on the activity series. Okay, that concludes question 97. The next question we had to do was number 104.
It says a solid sample of zinc hydroxide is added to 0.4 liters of 0.5 molar aqueous hydrobromic. The solution that remains is still acidic. It is then titrated with 0.5 molar sodium hydroxide solution. And it takes 98.5 milliliters of the sodium hydroxide solution to reach the equivalence point. What mass of zinc hydroxide was added to the HBr solution? So what they did is they titrated an acidic solution with base, but they didn't add enough base. And then they reached the equivalence point by finishing off the titration with a measured amount.
You're right, it's kind of it's not too long, just have to keep a few things straight. Let's start by writing what's going on chemically. Number 4, question 104. The chemical reaction is zinc hydroxide, a solid, is reacting with hydrobromic acid, aqueous. And it results in the formation of zinc bromide, probably a solid, plus water. We have a concentration of 0.5 molar of hydrobromic acid, and we've added 0.400 liters of that solution. So the number of moles of hydrobromic acid is going to be given by N is equal to M times V, where M is the molarity, V is the volume, and that's going to be 0.5 molar times 0.4 liters of solution, or 0.2 moles of HBr. Oops. 0.200 mole of HBr is present. They initially added an additional amount in another reaction where they titrated the remaining HBr with sodium hydroxide. So there was still some HBr left in solution, but now they used NaOH to titrate it. The reaction that results is going to give you sodium bromide, which is probably soluble, and obviously water as a byproduct. So now the amount of NaOH they used was 0.5 molar, and they used 98.5 milliliters to finish the titration. Again, using N is equal to MV, the molarity is 0.500. It's a funny looking M. Times 98.5 1/1000ths of a liter. So that's going to give you 4.925 times 10 to the minus 2 moles of NaOH was used, and because it's 1-to-1, it's going to give you the same amount of HBr was present. So times 1 mole HBr for every 1 mole of NaOH. If you really want to go through that, to show that step formally, you can do that, but it gives you the same number because it's 1-to-1. So 4.925 times 10 to the minus 2 moles of HBr was left. It was still left. So you had 0.2 moles, and then you proved that there was an additional 4.925 times 10 to the minus 2. So the total Oh, wait a minute. I just realized something. This is 0, this is a 1 to 2 stoichiometry. So that means,
The solution is still acidic. It is then titrated with sodium hydroxide.
so you gotta have the total, okay. That much HBr will titrate half as many moles of zinc hydroxide. So, so they over-titrated, and it's, what they did is called a back titration, okay? So this was a solid sample. They added this number of moles of HBr, but they overdid it. They over-titrated, okay? They over-neutralized the zinc hydroxide, so now what they had to do is bring it back by adding some more base, okay? But I just realized in here that the number of moles of acid is going to be twice as much as the moles of base. So there was 0.2 moles of HBr, therefore there's 0.1 mole of zinc hydroxide. Okay? Because there's two equivalents of this. I forgot to put that zinc hydroxide has a 2 here. Alright, so it's a 2 to 1 stoichiometry. So with that means you had 0.1 mole of zinc hydroxide in the original sample, and then you had to back titrate it with that many moles of HBr that was left. So from the 0.1 moles of yeah, I account for the stoichiometry later. So that we don't have to actually worry about that. Let's just only focus on the HBr that way. So I had 0.2 moles of HBr and 0.4925 moles of HBr was still left that had to be back titrated. So therefore, 0.2 moles HBr minus 4.925 times 10 to the minus 2 moles of additional HBr to be titrated equals 1.5075 times 10 to the minus 1 moles of HBr was actually present, which reacted with the zinc hydroxide. Now, that number of moles times 1 mole of zinc hydroxide for every 2 moles of HBr gives you 7.5375 times 10 to the minus 2 moles of zinc hydroxide present. And they're asking you for grams, so we're going to multiply by the molar mass of zinc hydroxide, which is combined made of zinc, 65.409, plus 2 times 15.394 for the oxygen, plus 2 times 1.00794 for the hydrogen, grams per mole. I'm running out of space. Final answer is 7.49 grams of zinc hydroxide was present in the original sample. Okay, that's what you call a back titration. So they overdo it, and then they back titrate to account for the actual amount that was present. All right, that concludes our mock test. I'm going to give you 1 day to look over the things that we did. Tomorrow I will post the real test for chapters 3 and 4. So tonight, spend some time studying, because that test is going to be worth 10% of your mark, and it could be worth more. If you do really well, I'm going to count that test. I'll give it more weight. Okay, so that should encourage you to really study for the test. And I'll see you tomorrow.